Hello Math 2, this is Mrs. Bricky, and this video is for Unit 2, Lesson 3. We're going to be talking about inverse functions today. So you know all about inverse operations. So today we get to learn about inverse functions, but we definitely will be using inverse operations along the way. So you know that the inverse operation for addition is subtraction, and the inverse operation for multiplication is division, and the inverse operation for power 2 or squaring is the square root. So some functions have an inverse. An inverse function is a function that reverses or undoes the actions of the original function. So if you have a function that takes an apple and turns it into a banana, the inverse function would take a banana and turn it into an apple. The notation for inverse functions is a -1 superscript. It's not an exponent, but it kind of looks like an exponent. So if you have function h inverse looks like this. And when we read this, we don't say like h -1 or something. We say h inverse. So literally the way that you read this little superscript is you say the word inverse. So the inverse of function k is k inverse. The inverse of function g of x is g inverse of x. And so you'll get used to that little notation, but it is kind of weird at first. So here's a table with some values for functions f and f inverse. Because we know that an inverse reverses a function, we can fill in some missing values here. So we know, for example, that function f takes a 5 as an input and outputs a 2, well, that means f inverse will take a 2 and output a 5. They reverse each other. And going up, for function f, the input 2 goes with an output 1. So for f inverse, if I input a 1, I'm going to get out a 2. For function f, if I input a -1, I get a 0. So for function f inverse, if I put in a 0, I get a -1. So if function f turns a -7 into an output of -2, function f inverse would take a -2 and output a -7. These two functions just reverse the actions of each other. And then we have, for f inverse, we have that, let's see, I want to look at this row. We have that f inverse has an input for an input of 3 gives an output of 8. So that means our original function f must take an output of 8, an input of 8, and give an output of 3. 11 would be the input to get an output of 4 in function f, because f inverse takes an input of 4 and gives an output of 11. They reverse each other. If you look at the graph of a function with the graph of its inverse, you can see that the values of x and y are interchanged. So if this function f goes through the point 2, 5, f inverse goes through the point 5, 2. So you get this symmetry where the mirror line is this diagonal line where y equals x. And sometimes it's hard to see the symmetry because it's a diagonal symmetry, but if you turn your head kind of diagonal, you can see the symmetry really well. So this function right here, the original function goes through the point 2, 1. The inverse function goes through the point 1, 2. For this one, we can see the f inverse goes through the point 4, 2. The function f goes through the point 2, 4. They are symmetric. Okay, so here's a function f. I graphed it in blue. It's the function 1/3 x plus 2/3. The inverse function for that particular function is the the line 3x minus 2. So we're going to graph that inverse function 3x minus 2. The negative 2 is the y-intercept, and the slope is the 3. We haven't really graphed a lot this year yet. So here's our y-intercept of negative 2, and we're going to count off a slope of 3. So that's up 1, 2, 3 over 1, 1, 2, 3 over 1, and we can draw that line. So this blue graph was function f. This green graph is f inverse. So in this case, I told you the equation of f inverse, but we want to be able to find the equations for the inverse functions. So here's a procedure that we can use for finding the inverse of a function. So you've got your original function. You need to think of that function notation as a y. I mean, that is what it is. It's a y value. We use f of x to name the function, but it is the same as a y. So our equation is y equals x plus 2. Now we know that a function and its inverse switch. They switch those x and y values. So we are literally going to switch our letter x, our variable x, and our variable y. Every x you see in the equation will become a y. Every y you see in the equation will become an x. And this is the inverse. It's just that we need to solve for y. So we want to isolate that y, and in this case, to isolate y, we just need to subtract 4. So we get x minus 4 is equal to y. That equation is f inverse. F inverse of x is x minus 4. And we could graph this equation. It's a line that has a y-intercept of 4, and the slope is 1. So up 1 over 1. And these two lines are inverses. You can see their symmetry, their diagonal symmetry. These two happen to be parallel lines, and they're exactly equally spaced away from that diagonal mirror line. You don't want to forget when you're writing inverse functions to give them the proper name of your inverse function. You don't want to just leave it as y equals. You want to make sure you name your function. That f inverse of x is very important. Okay, let's find this inverse and graph it. We have the function f of x equals 2x minus 4. Remember, we think of this this f of x as a y. And we need to switch the x and y values, and then we're going to solve for y. So this y becomes an x, and this x becomes a y. Everything else in the equation remains the same. We just literally replace the letter x with the letter y, and we replace the letter y with the letter x. Okay, so we are going to solve for y. In this case, we're going to start by adding 4. So we have x plus 4 is equal to 2y, and then we need to divide by 2. So dividing a binomial by 2, you need to remember that that 2 is dividing both terms. So we would write this as 1/2 x plus 2. And then don't forget to name that inverse. F inverse of x is 1/2 x plus 2. When you get to this step, if you just want to put the f inverse of x there instead of the y, you can. Here's my inverse function. If I graph that, that is a y-intercept of 2 and a slope of 1/2. There is f inverse. Original function f shown in blue. Okay, so those were both lines. We are also going to find inverses of some more challenging functions and also just some lines that are a little bit more challenging than the ones we've done to start. So we're going to keep doing some inverses here. We want to find the inverse of function g. So remember, this is our y. So we're going to switch the x and y. Everything else in the equation remains the same. That is our inverse. We just need to solve for y to put it in function notation. So we have x minus 3 is equal to 1/4 y. Now, sometimes I have students that are like, okay, now we need to divide by 1/4. Dividing by 1/4 gets you into this world of compound fractions that look really ugly and gross. So I would encourage you to not think of this as dividing by 1/4. It's really challenging to simplify and make it look nice if you do that. Instead, realize that timesing by 1/4 is the same as dividing by 4. So what we really want to do is multiply both sides of this equation by 4. When we're multiplying this binomial x minus 3 by 4, you probably want to put that in parentheses so that you don't forget that the 4 is also multiplying by the 3. And then on this side of the equation, the 4's cancel out and we're just left with the y. And so this is our inverse function. G inverse of x is equal to 4x minus 12. Okay, this is our first new function type. Function h of x is the square root of x minus 3. So we're going to switch our variables here and get the inverse relation. We've got x is equal to root y minus 3. Everything stayed the same in the function. We just literally switched the variables. So we want to get that y by itself. Well, right now that y is under a root. So we need to use a power of 2 to undo that root. So now we have the equation x squared is equal to y minus 3. And we're ready to finish up solving for y by adding 3. So we had an x squared and we added 3. So we now have an x squared plus 3. That's equal to y. And so our inverse function, h inverse, is x to the power 2 plus 3. So whichever operations you see in your original function, you have to use their inverses to find the inverse function. The thing to be careful of is just to make sure that you do the steps in the right order so that you end up with the proper inverse. On this one, for example, we don't want to start here by adding 3 because that minus 3 is underneath the root. We need to clear the root first. So just be mindful of your order of operations on these. Okay, so k of x is equal to x plus 1 squared. So this is a function that has a power of 2. So we are going to switch those variables. X is equal to y plus 1 squared, and we're going to solve for y. Right now, y is inside of a squaring, so we need to undo that with a root. Now, when we're finding a function, we technically maybe would have a plus or minus symbol here, but what we would really have is that we have two potential inverse functions. The negative root x is equal to y plus 1, and positive root x is equal to y plus 1. So we do technically have these two functions we could find. However, unless specified, we can always assume that we're looking for the positive function. So we don't need to worry about this negative one because we're just going to find the positive inverse. Okay, so we're almost done. We have one last step. We need to subtract 1. Now note, I'm subtracting 1 after that root was already applied. So that minus 1 is outside of the root. Make sure you can see that that negative 1 is not under the root, because it is not. So our inverse function, k inverse, is equal to the square root of x, subtract 1. Okay, this is our last line. M of x is equal to 3/4 x minus 2. So we're going to switch that x and y. So we have x is equal to 3/4 y minus 2. We need to solve for y. So we're going to start by adding 2. X plus 2 is x plus 2. And right now we have 3/4 multiplied by y. Well, don't let fractions get the better of you. What this means is that y is multiplied by 3 and divided by 4. We need to undo both of those things. So we need to divide by 3 and multiply by 4. That's the same as, you can think of it as multiplying by the reciprocal. Since this is a binomial over here, I need to throw it into parentheses. That 4 cancels, that 3 cancels. So if I go ahead and distribute this, I have 4/3 x plus 8/3. That's our inverse function. M inverse of x is equal to 4/3 x plus 8/3. Okay, so anytime we are given two functions, we could verify whether or not they were inverses via composition. I mean, we could, of course, just find their inverses and see if their inverses are each other, but composition is kind of a slick way that you can verify whether or not two functions are inverses. If two functions f and g are inverses, then if we compose them together, f of g of x and g of f of x, in both cases, it should simplify to be x. So we're going to check both of these, f of g of x and g of f of x. F of g of x means that we have function f, which is 4 times the input plus 2, and the thing we want to sub into f is g, 1/4 x minus 1/2. We're going to distribute. Well, 4 times 1/4 x is just 1x. 4 times negative 1/2 is negative 2. So we have x minus 2 plus 2. Those 2's cancel out, and we're left with just an x. So far it's looking good for these two being inverses. We want to do the other composition, g of f of x. So in this case, I have function g, and the thing I'm subbing into function g is function f. Well, I'm going to distribute and simplify and see if I get x. So this would be 1/4 times 4 would just be x plus, and then 1/4 times 2 is 1/2. And then I also have this minus 1/2 over here at the end. And you can see that those do simplify and add up to give you x. So we can conclude that yes, f and g are inverses. Here is another pair of functions f and g. We have the square root of x plus 5, and we have an x minus 5 squared. So f of g of x means that we have our f function, and we need to input g. And I kind of ended up with an extra parenthesis there. So interestingly, it almost seems like these two might be inverses, but when you substitute in, you get into this situation where you can't cancel out the 5's because this 5 is underneath a power or in a binomial that's squared. I mean, we could square out the x minus 5 to see if we could cancel something. X squared minus 10x plus 25. And then we have this extra 5. That's all under a root. And you can see that these two can combine, but this just can't really simplify. So we can probably conclude that these two are not inverses. But let's try g of f of x just in case. That's the input minus 5 squared. And if we put in the x plus 5 under the root here, you can see again we have this situation where we wish we could cancel those 5's out, but this positive 5 is under a root. It's kind of locked in there, and so it can't cancel out with the negative. So these two are not inverses. Their composition does not simplify to be x, and they are not inverses. Well, what if I had that same f function, f is equal to the square root of x plus 5, and my g function changed to be x squared minus 5? Let's try composing those. So we have function f, and the thing we're going to input into function f is function g. And now you can see that because function g changed, we can cancel out that 5. And so we have the square root of x squared, which simplifies to x. So that one worked. And then we have function g, which is the input squared minus 5. We're inputting root x plus 5. Well, the root and the power cancel, so I have an x plus 5 minus 5, and that is just x. So yes, these two are inverses. And if you look back at those two g functions, the only difference really was the order in which the operations were applied to x. The first g was first to subtract 5 and then to square, and this one on the screen right now was to square and then subtract 5. So the order that your things are happening in your functions and your inverses really matter. Okay, that's it. You should have an assignment in your packet. If you have questions, let me or your teacher know. Thanks a lot.